How does a compiler work? From source code to ones and zeros that your computer executes. In this video, these are the questions we're going to answer. What is a compiler? Why are compilers important? What's the difference between an interpreter and a compiler? How does the compiler fit into the bigger picture of running programs? And what are the 5 phases of compilation? Before a program can be run, it must first be translated into a form that a computer can execute. The computer is really just a big calculator attached to a large memory. And the computer only understands sequences of ones and zeros called machine language. The system that does this translation is called a compiler. So, how's this going to make you a better programmer and engineer? You need a compiler to make a computer execute your code. Knowing the ins and outs of this system will help you understand and fix errors more effectively. The way a compiler works also helps us understand how computers process speech. Knowing the difference between a compiled versus interpreted language will help you understand when to use each language. For example, why are game engines and operating systems written in the C programming language and not in Python? Well, Python is interpreted, so it's relatively slow to execute, while C is compiled. An interpreter is another kind of language processor, but instead of compiling the whole program and then running it, it appears to compile and execute statements line by line. Python and JavaScript are examples of interpreted languages. These are generally slower to execute than compiled languages because this translation from source language to machine code, which is then executed, that translation is done line by line, and it is done every single time we run the program. With a compiled language, we just do that process once, and then we can just run the machine code every time. So if interpreted programs are slower to run, why would we use them? Well, first of all, they can be run on any machine without further processing, and when the program is running, the interpreter can run diagnostics and speed the program up as it is running, so it can make optimizations on the fly. Also, the distinction between an interpreted and a compiled language is not always so clear. Java, for example, is both compiled and interpreted. The compiler will translate your Java program into an intermediate representation called bytecode. Humans can't read or understand bytecode, but it is very machine-like. This is useful because it does a lot of processing up front. This bytecode is then interpreted in a virtual computer called the Java Virtual Machine, or JVM. It's just an emulated computer that runs the same way on any CPU, any architecture. So this is why the same optimized bytecode can be executed on any machine as long as it's running a JVM. Now, as the bytecode is interpreted by the JVM may compile certain parts of the program that are executed a lot, so it can speed it up. This is known as just-in-time compilation. So it is both interpreted and compiled at the same time, even after it becomes bytecode. So as a comparison, with the C programming language, you have to compile it for every kind of computer that you're going to run it on. If I want to run my C programming language on an x86 processor, I have to compile it for that one. If I want to run it on an ARM processor, I have to compile it for that one, and those two outputs will be completely different. Now, how does a compiler fit into the whole picture? Other pieces that are not the compiler may be required to create our final machine language executable. The source program may be divided into separate files, so we need a preprocessor to collect these separate files and put them together into a final source file. The preprocessor can also expand abbreviations called macros into source language statements. This modified source program is then fed into the compiler. The compiler then produces an assembly language program as its output. Then an assembler gets this assembly language program and finally produces the relocatable machine code as its output. With large programs, we may have to compile it in separate pieces, so this relocatable machine code may have to be linked together with other relocatable object files and library files into our code. The linker resolves external memory addresses, which is when one file may refer to a location in another file. The loader is the final step of this process, which puts together all of the executable object files into memory for execution. So now that we know how the compiler fits into the whole picture, let's talk about how the compiler itself works. We can think of the compiler as having two distinct parts, analysis and synthesis. The analysis, or front end, understands what the programmer wants to be done and will report any errors along the way. The synthesis part, or backend, is what creates our final output. Furthermore, the compilation process is split into 5 phases. The first phase of the compiler is called lexical analysis, or parsing. It reads the stream of characters that make up the source program and groups the characters into lexemes. For each lexeme, the lexical analyzer produces a token of this form. In this token, the first component, the token name, is an abstract symbol used during syntax analysis, and the second component, the attribute value, points to an entry in the symbol table for this token. The second phase of the compiler is syntax analysis, or parsing. It uses the components of the tokens produced by our lexical analyzer to create a tree-like intermediate representation that demonstrates the grammatical structure of the token stream. A typical representation is a syntax tree. In this tree, each interior node represents an operation, and the children of the node represent the arguments of the operation. Phase 3 of our compilation is semantic analysis. The semantic analyzer uses the syntax tree from the previous phase and the information in the symbol table to check our source program for semantic consistency with the language specification. In other words, it makes sure that things are written correctly and will throw an error if that's not the case. It will also gather type information and save it in either the syntax tree or the symbol table for later use during our intermediate code generation. An important part of this analysis is type checking, where the compiler will check that each operator has matching operands, and in some cases it may do a coercion, which means it's going to convert a type automatically for you. Phase 4 is intermediate code generation. With our syntax tree as input, the compiler creates an explicit machine-like intermediate representation as output. This intermediate representation should be easy to produce and easy to translate into the target language. A great example of this intermediate representation is the bytecode that we talked about earlier, which the Java compiler creates. This bytecode is easy to translate into our final machine code output, and once again, that bytecode can be run by any Java virtual machine. The next phase of the compiler is the optional code optimization phase. We get the intermediate representation and apply optimizations to it so that the computer has to do less work when it runs our program. For example, the int to float operation can be eliminated entirely, and we simply replace our integer with a float and use that in our final assembly code. This phase is optional because our code can still run without optimizing it. When we're just developing our program, we may not want to spend the time on code optimization, but when we're ready to create our final output and we're ready to publish our program, that's when we may want to do our code optimization. The final phase of our compiler is code generation. It takes as input our intermediate representation and maps it onto the target language. This is the synthesis part that we talked about. If the target language is machine language, memory locations or CPU registers are selected for each of the variables used by the program. Then the intermediate instructions are translated into sequences of machine instructions that perform the same task. So, those are the 5 phases of compilation. Our assembler would then grab the output of our code generation and turn this into our machine language, which is finally run by our giant calculator, aka the processor. I hope this video gave you a deeper understanding of what goes into translating the English-like programming languages that we use into the ones and zeros that our computer finally executes. Please like the video if you learned something, and comment below asking me what other programming topic you'd like me to explain. Thanks for watching.